Hi, so if you have been watching the Introduction to Embedded Systems series on this channel, then you know that there is one big subject that we have left to the end, and that is security, which is a vast subject, especially if you don't want this guy to take over products that you have fielded, hack them, and use them for all kinds of malicious actions. So in this video we're going to show a short summary of what is security for embedded systems, and make sure you watch this to the end, because at the end we're going to see a holistic example, which is the Pathfinder Mars rover, and what an incredible system it is, with many characteristics intersecting with what embedded systems are. So keep watching.
Of course, there is no way on Earth to talk about embedded systems without at least mentioning security. This is a vast subject, so I will only be touching it. Let's see some of the security challenges we have in embedded systems, but we definitely cannot see all. Each one of the systems we deploy is susceptible to a range of attacks. In the remote attacks group, we can list as examples buffer overflows, denial of service, and data leakage. What those are exactly is beyond the scope of this talk, but let's see in a nutshell. Buffer overflows are when we fail to check the size of buffers against what they are supposed to hold. An attacker can potentially use this to inject malicious code and run it on our system. In a denial of service attack, an attacker will bombard a system with requests until it can no longer service others. Data leakage occurs when items that are supposed to stay concealed in the system leak out. Since anyone can buy one of our units, we assume physical access too. This means that an attacker can replace flash content with malicious code, read files from flash, or even try to peel layers from chips in order to see internal logic and secrets. Our systems are spread in the field, possibly containing our secrets or the client's secrets. Can an attacker get his hands on a system and extract such secrets? Can an attacker use our hopefully vast number of systems as a botnet for his attacks? Do they contain vulnerabilities that jeopardize networks hosting them? Let's look a little deeper into those risks. Let's talk about what an attacker can get out of our system. Some IoT devices are so poorly secured that they can be easily detected on the network, and they will give out potentially harmful information through remote API calls. In general, IoT devices are almost identical to each other when they come out of the factory. Could it be that they contain global secrets under flash, like keys for example, that can compromise all units of the same model? If yes, how are those secrets stored on the device? In general, one has to assume an attacker will be able to physically read and reverse engineer the flash content. Did we prepare our design for that option? Let's look at a test case, the Mirai botnet malware. Mirai is targeting Internet of Things devices specifically. So what is a botnet attack? Imagine a brute force attack on a website trying to guess a password. An attacking system may try all the combinations, but the system under attack will limit the number of trials from a specific IP address, therefore limiting this attack. One way around this is to divide the passwords to many chunks and use a huge number of systems to attack each one with the chunk. You can do that if you get hold of a vast number of systems. Another thing you can do with a large number of systems is a denial of service attack. You can send requests from a huge number of sources, bringing the target system to its knees. You can do that if you get hold of a large number of systems, and deployed embedded systems are nice candidates to become part of an attacker's botnet. Mirai is a malware targeting IoT devices specifically, with variants still active today. Mirai crippled the US East Coast Internet services in 2016 with a denial of service attack. Mirai works by probing IP addresses for IoT devices in a brute force manner. When a device responds, Mirai will attempt logging in and taking over it by using tables of known default passwords. Many thousands of IoT devices out there still use the default passwords, so Mirai has no difficulty in taking them over. Once that is done, Mirai is active on the device, purging competing malware, and staying in contact with the command server to get attack jobs. Why are IoT devices such a great target to become part of a botnet? Because you have a vast number of them, which is good for both finding unsecured systems statistically and also to create large attacks. IoT systems are connected and many times poorly secured. It is more likely to remain unnoticed after infecting an IoT device than on a desktop or a laptop. Devices are also well known and identical to each other, so you can hack one and know all the others. Let's see a case study where attackers infiltrated the database of a Las Vegas casino. For more details, you can Google the words hack casino thermometer. The story goes like this. An attacker hacked an IoT thermal sensor in the casino's aquarium. Once a foothold inside the organizational network was established, it was possible to continue into the rest of the network and into the database. Then the attacker could pull out the database content back through the same chain. So you see, a poorly secured device jeopardized the entire organizational network. So when building your system, your responsibility is not just to secure the data on your device or to prevent secrets from leaking from your device. There are more high-level ramifications you have to take into account. Let's discuss what we just saw. IoT and embedded systems are easy prey to attackers. This is partially because each design is a specific solution tailored to a specific problem, which means that every design is a new design potentially. This opens the door for more security issues. Mix that with pressing project times and competing business priorities, and you may get a product that is minimally secured, if at all. On top of that, the feature set we have on big computers, like the latest Intel processors with all the latest and greatest in security, is not what we will have on a small system. It's true that some microcontrollers, for example some of the ARM processors, have strong security features. However, other popular smaller and cheaper microcontrollers may have no memory protection, no NX or no execution mode for memory, not even CPU kernel mode. Add to that systems are not necessarily in a person's reach or even eyesight, not necessarily updated unless we force the updates, and not necessarily showing any issue after being hacked. And mix all that with a vast number of connected systems, and you get yourself the perfect victim. In the solutions department, I chose to touch one area in the vast field of securing embedded systems, mainly because this area looks cool to me. I am about to talk about secure boot in embedded systems. One of the holy grails of attacking a system is the ability to inject and run malicious code. If we look back at how our image is built, assume the green module is the one the CPU starts executing, then it loads the orange one, that in turn loads the yellow one. Each load operation begins with authenticating the loaded entity's digital signature. If an attacker manages to replace a module or modify it in any way, the authentication will fail and we can potentially take a special path or refuse to boot. However, authenticating the bad module in this picture is done by the orange module. What happens if the attacker tried to modify the orange module itself? Well, it is authenticated by the green module, right? You see where this is going. As long as the attacker can attack the beginning of the chain, the rest is assumed to be compromised. Secure boot is about being able to create a chain of trust. The boot begins with having the first lines of code run from a trusted piece of firmware. One way to do it is to place the initial code in a non-changeable location like ROM memory or one-time programmable fuses. The first running entity is usually small, since it is not desirable to have a lot of unchangeable code in the design. If a bug is found in non-changeable code, it could be devastating to the product because we cannot fix it. So the role of this first entity is just to authenticate and run the first changeable entity, usually residing in Flash. This entity will then continue the chain into loading the rest of the modules. At any given moment, no untrusted code can be loaded and run. we end up with a trusted boot chain. I have mentioned before that we should consider attackers getting their hands on our product trying to attack it. One of the things they will definitely try to do is to inject their own binaries to the unit's flash, trying to get the first boot stage to load it and compromise the rest of the firmware. With secure boot, done correctly of course, this option is denied. I cannot emphasize enough how deep the field of security is, and that whatever I try to do here will barely scratch the surface. Security deserves several hours by itself. I hope the various examples we have examined have just given you a taste of it. Let's wrap up this talk with a really awesome test case, that of the Pathfinder project to Mars. While the spacecraft is on Mars, the control team on Earth noticed interruptions in the data stream. They discovered it was caused by multiple watchdog timer resets. How did they discover this? My guess is that they had a good logging system that indicated this. After an investigation that included working on a similar system on Earth, they have found a priority inversion bug. Explaining what is a priority inversion bug is outside the scope of this talk, but in a nutshell, it means that high priority threads are not getting runtime because of actions taken by low priority threads. The system was using VxWorks as its operating system. They came up with the solution and was able to patch the system on Mars with it. What a magnificent example of great engineering. What do we take from this example? Pathfinder was built to survive. The resets probably prevented it from getting into a bad state permanently, perhaps losing contact with Earth. It was instrumented with what is needed to understand what is going on and to debug the issue. It also included ways, which for sure were secure, to fix the unit in the field. My take from this is, build robust systems, prepare for bugs as you will always have them in complex systems, and make sure you have the right tools to deal with them when they come up.
Alright, so I hope you have enjoyed this video and the rest of the series, and I hope you find the strength in yourself to like this video, and I also recommend that you subscribe to this channel because there is other great stuff about embedded systems coming up. See you!